There we go. Alright, so the new link should be working because I can see myself using the new link. Yep, there we go. Yeah, so alright, so this is kind of embarrassing because I have a really wimpy laptop computer. And since COVID, it's basically serving the need of a desktop computer. And I was trying to learn how to do game programming. It cannot happen without a GPU. So I used the Thunderbolt 3 port to hook up to an external chassis that has a GPU in it, that has a graphics card in it, and my hand just swiped, just knocked off the USB 3 cable. That obviously caused the operating system to be quite upset about it. So there we go. So probably have to kind of watch my hand and not to knock that cable off again. All right. So back to operator error, not malfunction, just just error. there's no excuse. It's just me being clumsy. Anticlimactic. Yeah, it is. Anyway, so we are back, and I am going to open up the usual thing. So there we go. Alright, so let me see how many of the tabs it kept, because I think it should keep most of the tabs or not. Yeah, I think it got confused. The window that we are seeing right now is not the one that I was using earlier, so I'm gonna have to sign into apps.losreels again. When they restore the windows, it just kind of randomly restore the tabs of the windows. So sometimes it would do it right, and sometimes it does not get it right. Alright, so there we go. It just takes a little bit longer. Get here. Alright, so we are back to binary addition. That's what we're going to be talking about today. And binary addition is down here. There we go. Alright, so I'm hoping you guys got a chance to review the material, especially when my computer just went down and took me like 7 minutes, 8 minutes to reboot. So I hope you guys used those 8 minutes to kind of review the material. So now you're all ready, you're all caught up, right? 8 minutes is a lot of time. So what we're going to do today is to talk about the equations. Okay, so let me just go ahead and summarize the equations first. The equations are here already. So if we want to look at the equations, there's a whole bunch of equations, that are kind of dispersed within these notes here. So it is really helpful if you can kind of collect all the equations, collect all the definitions, particularly the definitions for base 10 and then the definitions for base 2, and just kind of stash it at one single place, because that is how you can kind of easily visualize that's how you can visualize the how each equation is used when we're computing one of the bits within the calculation that we talked about last time. And the markdown file from last time, from last Thursday, is already on the channel, so you guys can actually go back and refer to it if you want to. So what I'm going to do now is I am going to, today is 0201, alright. Yeah, it's going to complain, and we'll just go ahead and delete that. There we go. So what I'm going to do is to summarize some of the stuff that we talked about before. So x and y are given. S is the sum. Oops, given, and then S is the symbol for the sum, is the sum. Alright, so everything in between is going to be the mysterious part. I'm hoping that you guys got the notes from last time. Okay, so this is another thing I want to kind of go over kind of quickly, is I can share these notes with you guys, not a problem. However, when you are watching me, when you are in the lecture, you probably should be taking notes as well. Now, what you write in your notes is entirely up to you, because it really kind of depends on what stands out to you, and you might want to write it down. The reason why, if I, even if I disclose my notes, even if I post all my notes, in Markdown, it still does not replace the process of you taking notes during the class. So you can use mine kind of like a fallback, okay, just in case you're not quite catching everything. But then the video is catching everything, right? Because my notes is actually completely displayed as I work on it. It is also here. So I think going through the quote-unquote trouble to take your own notes is actually beneficial in the long run. In the short run, it seems like if I just kind of type my own notes and I post notes from me to the whole class, you can save some time. In the long run, the process of taking notes is actually, I think it's important in the process of retaining, that's it, retaining the material, and also kind of deepening the understanding of the material. So that's just that. All right, so now we're going to move on to the intermediate rows. Okay, so Q is the single digit sum of x and y. And then we have the K row. There was a little discussion of what K means. K really means carry. Okay, K for carry. I know it is an intentional typo, but I don't want to use the same name as the function itself, because we have a function called C, and C is not the overall carry, because C is only used to say, okay, if we're adding the x and the y bits, is that gonna give us a carry? That's one application of the C function. And then we also have to apply the C function again to the Q and the K bits of the previous column. So C is really just a function. It takes two single digits, and it tells us the addition of those two single digits, would that end up with a carry. That's all what the C function is doing. But it doesn't tell us whether there's a carry to the next column or not. And that's why I need to distinguish between the K bits, which is actually whether we have a carry to the next column, as opposed to whether the C function is telling us that, oh, if you add these two single digits, you can end up with a carry. So that's why the K is different. All right, so K is the carry bits, okay, from to a column. So they have components, as we'll see later on. So those are the these are the symbols, to kind of refer to the different rows. We have X, Y, and then Q, and then K, and then S for sum. So now the question is, how are they related? Okay, what kind of function do we use to relate these? So Q of I is the easy one, because Q of I is really just the R, the single digit sum of xi, yi. There we go. So that's how Q is defined. And then K is harder, okay? Because let's deal with the other easy one first, okay? Because the sum bit is also very easy to to figure out, because that's the single digit sum between the Q bit and the K bit of the same column. So as you can see, the R function can be applied at different places, and it will give us a different portion of the addition. So now the question is, what about the K bits, right? The K bits is actually going to be the one that is kind of more interesting, because when you look at the K bits, I typically refer to Ki plus 1. In other words, it is the column next to where the calculations are occurring. So this is going to be the C function applied to xi, yi. And then we have an OR. So this plus here is really, in this context, it means OR. Okay, so OR the C of Qi and Ki. There we go. Now, don't write this down. There's no need to. Well, okay, write it down, and stash it somewhere. But if you're thinking about, where this is coming from, it's all in the module. Okay, I have not introduced a single new concept aside from what is already in the module. So if this stuff is looking a little foreign, if this stuff is looking like, okay, where did we define the R function? Where did we define the C function? And what is K doing here? Well, I think you guys already know what I'm about to say. It's time to review the material because all of this stuff here we talked about last week already in base 10 and also in base 2. Okay, so in base 2 we got something that's also kind of special. Once again, nothing new. This is all stuff that we have already introduced. So in base 2, in other words, this does not apply, for base 10 cases. So in base 2, C of something, I'm not going to use XY here. Let me go pick another 2 symbols so that we can refer to these things. And I don't want to use M and N. Okay, so I got to think of which letter is not being used, and we can use those. Let's see. G is going to be used later on. H is okay. J is probably okay. So we can use H and J. So H and J are really just 2 bits, okay? Because remember, C is only useful when you are giving it single digits. In base 10, a single digit is going from 0 to 9. In base 2, a single digit is going to go from 0 to 1. So H and J are Boolean. Okay, they can only be 0 or 1 or true or false if you want to. So in this notation, this is how I'm going to say it. Okay, this is just a conjunction between the bits of H and J. Now, if somebody looks at this and go like, but that looks like multiplication. When did you say that conjunction can look like multiplication? That was a long time ago. Okay, that was week 1, I believe. So that's 1, and then the K function, this is the C function. The R function is basically exclusive OR, and if you cannot do exclusive OR because you say, but there's no single operator, logical operator for exclusive OR, then we can do something like this: not H and J, or not J, H and not J. So that would do exactly the same thing. You negate one and then and the other one, or you basically do not negate the first one and then and the negate the second one. They would give you the same thing. Okay, because this R function is going to do the trick. So up to this point, it really is a review of what we have talked about. Okay, so. If this does not feel like a review, then we need to talk about it, okay? Because that tells me that something needs to be changed. Because otherwise, this is going to be a very long and painful semester. I'll just be honest with you guys. It's going to be long and painful if you look at this stuff here, and you just go like, I have no idea what that is. Okay. All right. So now what we're going to do. I'm just looking at the time here. Okay, I'm gonna have to change the order a little bit because I would like to cover the material enough so that you can start with your lab tonight. So I'm gonna switch things around a little bit, and we're gonna go straight to carry look ahead. Okay, but we're gonna keep these things around. Okay, but instead of talking about the carry ripple adder, which Jonathan actually covered in his beacon session yesterday, we're gonna jump right to section 6. So section 6 says, but wait, there's more. Well, that's typically telling you that there's a whole lot more. So what we're going to do is to get back to the definitions of how we compute k of I plus 1, which is exactly what you see here. And then there will be a little bit of Boolean algebra here, a bunch of manipulation of the symbols using algebra, so to speak. So is VI like coding using regex? Nope. VI just uses regex for search and replace, or just search by itself. But it definitely has regex in it. All right, getting back to our main topic here. So from the first row to the second row, that's really just using the definition of the carry function. And as my notes here has already indicated, the C function is really just a conjunction. I mean, it's that's how we compute whether the addition of two single digits in base 2 ends up with a carry or not. So from the first row to the second row, that really just has to do with the carry function being conjunction by itself. And then from the second to the third row, that has to do with how Q of I is defined. So Q of I is defined here, which is R of xi, yi in general. That is not specific to binary. When it is specific to binary, then we say R of xj is basically the exclusive OR between those two bits. But from here to here, that is generic. Q of I is just R of xi, yi. And then from here down, I'm expanding R of xi, yi so that it becomes xi and not yi, or not xi and yi, which is also consistent with a quick revisit of how R is computed using Boolean operators. And then from here to here, it is called distribution. So as it turns out, Boolean algebra, just like normal algebra, has distribution. So we are just doing a distribution here. It depends on the context, Eric. So it depends on where that in general is. After we're done talking about this, yes, I'm waving my hand again, but this time it's my right hand, so there's no chance that I will be touching the cable again. So after we're done with this part, we can go back and look at the context of that, in general. All right. So going from here to here. Now this is not strange, right? Because we have xi, yi originally, and then now we have xi, yi and true. Anything and true is just that anything that you started off with, so it doesn't really do a single thing. And then from this row to this row here, this one doesn't make sense if you are not dealing with Boolean algebra, because in normal algebra, in arithmetic, this doesn't make sense. How can this one be 1 plus something? They certainly would not be the same when you're dealing with arithmetics in general, because your k of I can be non-zero. However, in Boolean algebra, that's okay, because we have true here, and a true or anything is always just true. So that's why you can always just replace a true with true or something. So you might be wondering, why would we do that? That just doesn't seem right. That doesn't seem smart. Well, that's because now we can say, from one single term of xi and yi, now we have xi and yi, or xi and yi and ki. So the reason why we are doing this is then we can do some reshuffling, at this point. Then from this row to this row here, it also looks mysterious, if you are used to just normal algebra. From this row to this row, it looks a little mysterious because I just replicated this term here. Xi and yi and ki is replicated over here. Now in normal algebra, that cannot happen. But in Boolean algebra, it's okay. Simply because if you have a Boolean value called k, okay, I shouldn't use k. Let's say you have a Boolean value called j, okay? J and j is j. J or j is still j. So you can basically use and or and replicate the term a whole bunch of times, and it doesn't matter, okay? It still gives you the same value. So I'm replicating that thing and then using the commutative law, which means we can exchange the ordering. As long as we're just doing a bunch of ORs, we can exchange the ordering. So I just moved that thing over here. So from here to here, I'm using the associative rule, which basically says I can put parentheses anywhere within the gigantic disjunction, because the order of applying the operator does not matter. Okay, that's what the associative law is saying. And then from here to here, this is factoring, because I recognize that both of these terms contain xi, ki in the conjunction. So I extract those two terms, on one side, and then use factoring, so that the only part that is different between these two conjunctions, which is yi coming from here, and then not yi, which is coming from here. So those two are extracted out, by factoring, and I do the same thing on this side. And then from here to here is simplification, because when you have yi or not yi, well, guess what? One of those two has to be true, right? Because they're negations of each other. And when you're in a disjunction, if at least one side is true, the whole thing has to be true. And this time we are guaranteed that one of these two has to be true. So this particular disjunction simplifies to true, and the same thing applies over here. And so anything and true is just that anything. So the one is now simplified away, and we ended up with xi and yi, or xi and ki, or yi and ki. And then I do one more factoring by noticing that ki is common to these two conjunctions. So I extract ki out, and then do the factoring, and we only contain the xi or yi over here, because those are the only components that are different between these two conjunctions. Alright, so we got a question in the text channel. I thought when it looked like they were multiplying, it was a disjunction. No, multiplying is a conjunction. A plus is a disjunction. You got it the other way around. Alright, so we got to get those symbols, okay? We got to get the symbols and definitions down at this point, okay? So I really urge everybody to have a table of summary of all the terminologies, okay? All the equations, all the symbols, everything that we have talked about up to this point. Because if we don't get the definitions or the symbols down at this point, I might as well just teach this class in Cantonese. Okay, maybe there are a few people who can actually understand Cantonese in this class, but generally speaking, that is not the case. Okay, I might as well just teach this class in Cantonese, because people who can, because the symbols are very important. That's the vocabulary. It's the basis of how we get the concepts across. Okay, so I really urge everybody to do what I just said. Okay, get all those definitions to one spot, so that you and study it too. Okay, make sure that you get to it, and the more you use the symbols, the quicker you absorb it. But that part is really important, because otherwise, it's not going to be productive. All right, so moving on. So now we have just one gigantic transformation, and k of I plus 1 is transformed into here. You look at this and go like, so what, right? I look at this and go like, yeah, so what? Well, okay, so there's one more thing here. Now, this is where you really need to get those definitions to one spot, because when I introduce the definitions, the equations and whatnot, I am introducing those things in the context where the flow of logic makes sense. So that is why they're all scattered, okay, all over the place, because it depends on the flow of logic. But when you need to refer to those things, you might want to put all of those definitions in one place, so it's just a whole lot easier to look up those definitions. So I'm going to give you a clue here, because we got two definitions coming up that are important. One is g of I. So g of I, by definition, is really just the conjunction of xi, yi. Okay, so that's by definition. That's how g of I is defined. P of I, on the other hand, is by definition the disjunction of xi, yi. So you might want to just do what I said earlier. Write these two definitions down, put it into a place in your notes, and say these are important definitions, because your lab depends on it. In fact, your lab actually depends on a lot of things that we just talked about, from the beginning as well. So, that's all going to be important. So, given that these two terms, g of I and p of I are defined like this, now we can rewrite k of I plus 1, because k of I plus 1 after this really long, derivation is just, xi and yi, or xi or yi and ki. Now that we have defined, g of I and also p of I, we can use those terms. So now k of I plus 1 is, g of I or p of I and k of I. Alright, so I'm just going to pause here because there's a lot of stuff that I just introduced, in addition to the review of the symbols, conjunction, disjunction, and the derivation stuff. Okay, but let me just kind of pause here and see if there are any questions. Alright, so factoring out gives you a conjunction of 2 added together to what is factored. Alright, so if you just focus on this part here, just this term here, and applying factoring, factoring is the reverse of distribution. The same thing in algebra as well as normal algebra. Okay, your Boolean algebra and normal algebra still has the same thing. It's just the reverse of distribution. Only question I have is how to apply these definitions. Well, we're going to get to it. Very good. But we're going to get to those. Okay, but for people who have read a little bit ahead of time, those people would probably get at least some idea of why these things are important. And that is why reading ahead is important. Last week I said you might want to finish reading the entire binary addition module. I know it is hard to dig through. I do know that. Okay. Yep. Okay, that's fine. Alright, so have I addressed all the concerns at this point, or is there anything that is still hanging? I'm just gonna write over here, how distribution works. It basically goes in both directions. So this is just normal algebra, okay, not even Boolean algebra, but it applies in Boolean algebra as well. Okay, so if you have AB times AC, that whole thing becomes, it is equivalent to A times B plus C. That's, it depends on which way you're going. If you go from right to left, it is called distribution. If you go from left to right, it is called factoring. And as it turns out, this works in normal algebra, but it also works in a Boolean algebra. So are we good there? Are we understanding the application of factoring? Alright, so this is all dedicated to working on the issue where the carry slows down the adding process. Yes, Omer is correct. We are not quite there yet, okay? But we are building up the vocabulary and the representation in order to get to the point where we can go like, look at this. I can make k of I plus 1 not depend on of k. No, take that back. I can now make k of I plus 1 not depend on k of I anymore. Because that's the whole thing. That's why it is so slow. It's because, hey, until you have k of 1 done, k of 2 may not be correct. Until you have k of 2 settled down, k of 3 may not be correct. So you're waiting. Each one is waiting for the one before to be fully computed, and that's why you have a linear dependency. So when you have 64 bits, okay, the last one, bit 64, is going to have to depend on a long chain of carry bits to settle down, and that's going to be slow. Okay, so we are trying to overcome that particular limitation, but we are not quite there yet. Okay, we are building up the P and the G terms because they are important in the derivation, to get that accomplished. All right, so Omer is correct. Okay, so that's a very good point because that gives the the discussion that we are having right now a context. So that's good. Oh, okay. Yeah, so the whole point is k of I plus 1 depends on k of I so far, right? And even if I use the g and the p terms, k of I plus 1 still depends on k of I. So you're saying, okay, what is this buying us, right? We are just doing a whole bunch of symbolic manipulation in Boolean algebra, and we still end up with this problem. So at this point, what we're going to do is we are going to work out a few of these things just one by one, okay? Because this I start from 0, but it can be 1, can be 2, can be 3, and so on. So we're going to start with what if I equals to 0, okay? When I equals to 0, we try to compute k of 1 from g of 0 and p of 0 and k of 0 in this particular format. So let me just kind of pause here, make sure that people understand that this equation here is really the general form, except we substitute I equals to 0 in this case. So if we are good here, then we can move on, unless but if there are questions at this point, then I will have to address those questions first. So are there any questions about k of 1 is g of 0 or p of 0 and k of 0? All right, so I'm not seeing any questions. Okay, so very good. That's good. All right, because it's just a substitution. Okay, all we are saying is let I equal to 0 and see what happens. That's all we are doing. Cool. All right, so we are going to move on to the next one. So the next one is, what if I equals to 1? So if you plug in I being 1, then we are computing k of 2, because 1 plus 1 is 2, depending on g of 1 or p of 1 and k of 1, which is exactly what the first row is doing. So the first row is really just the result of substituting I with 1, and then we just get this concrete case over here. And then what we do next, now that is the key to this entire thing, okay? Because what we're doing next is to say, hold on a second here, we know what k of I is. So k of I, according to this, is g of 0 or p of 0 and k of 0. So I just expand k of 1 to the expression that computes k of 1. That's how we got from the first row to the second row of the proof. Do we have any questions about how we got from the first row to the second row? I'm just looking at the text channel. All right, so no questions. All right, good, good. All right. All right, so we're good. So now we use, well, okay, tell me again, how do we call this again, going from the second row to the third row? Starts with a D, by the way. Exactly, it's distribution. So we are basically just doing this, okay, except it's from right to left. Okay, so we start with something like this, and then we end up with something like that. All right, so we look at this and go like, well, K2 doesn't depend on K1 anymore. Instead, it depends on K0 and a bunch of the P's and the G's. All right. Okay, well, that's okay so far. Okay, I'm just looking at the time because I need to make sure that I got enough time to explain why this is a good thing. But we're gonna keep going a little bit, and then we're gonna go back and talk about why this is a good thing. So now we look at what if I equals to 2? So when you plug in I equals to 2 over here, then 2 plus 1 is a 3. So k of 3 depends on g of 2, P of 2 and K of 2. Exactly like this, right? The first row is really just from not expanding, but substituting I with a constant of 2, and then we end up with the first row. The second row is just going like, hey, but we know what K2 is. Here's K2. K2 expands to this particular term here. And so we just do a substitution. So we just go like, hey, we don't need to write this as K2 anymore because we know how K2 is computed by an expression. So we put the expression in here. And then we apply distribution again. Okay, so after we apply distribution, we end up with the last row. Okay, so now we have 3 carry bits. Okay, K1 is this, K2 is this, and then K3 is this over here. So when we do it, okay, we look at this and go like, oh, this is not any easier. Okay, sure, K of 1 is the only one that depends on the previous one because that turns out to be K0. K of 2 doesn't depend on K of 1 anymore, it just depends on K of 0. K of 3 does not depend on K of 2 nor K of 1, it only depends on K of 0. So now the question is, how is this any better? Right? I mean, how is this any better? So the reason why this is better is because unlike when we do calculations, we have to do everything sequentially. When you use gate logic to perform the computations, a bunch of stuff can happen at the same time. So if you just look at all the P and the G bits, okay, G is defined to be the conjunction of X and Y. Now remember, all the bits from X and Y are inputs, so they are ready, they are available, they are here for you to use from the get-go. Okay, so all the bits, all the XY bits are already here at the very beginning. So is K0 because K0 is also an input. So that means the first thing we do is we just use a whole bunch of AND gates to compute all the G bits, a whole bunch of OR gates to compute the P gates, right? To compute the P values. So all of those can be done simultaneously. There's only one gate propagation in order to do this. Now let me start up Logisim because I think in Logisim it will be easier to understand what I mean by that. Well, but I don't want to give you the solution of today's lab also. So that means Alright, so I know how to do this. Okay, so I am going to present the same type of reasoning, except it's not going to be in gates because you're going to have to translate all of this in gates. Okay, so I'm going to say for I going from 0 to whatever bit, n, n minus 1, so n is the number of bits that you are that you have in X and Y, and also the sum. So we're basically doing an n bit adder in this case. So for I being from 0 to n plus n minus 1, use n AND gates to compute g of okay, I'm going to use equations here to compute g of I all at the same time. Okay, so does everybody understand what I mean by this? We basically use AND gates. The first one will handle x1 x0 y0. The next and then we will handle the next one's going to handle x1 y1, x2 y2, and so on. And all of these gates can operate at the same time. So are we good with that concept? This is done by a multi-bit gate. So in Logisim, okay, instead of doing a whole bunch of tiny little AND gates, you use one single AND gate and then you make a multi-bit AND gate. Alright, so that's why we talk about multi-bit stuff in the previous lab, because we're going to use that concept today in order to say, well, do you want to have a whole bunch of gates where there's actually a structure to how to compute the output, okay, maybe we'll just use a shorthand by using a multi-bit gate. Alright, so in the text channel we got a few things. So this process is faster only because we are using logic gates. It's more like the logic gates are computing in parallel. Okay, so a bunch of gates are doing stuff in parallel. So in this case, I'm gonna write it clearly. So all these AND gates operate at the same time using only one propagational delay to have all the G of I bits computed. Alright, so obviously there's one term that we have not seen before, which is propagational delay. So what this term is referring to is there is a delay, okay? When the input of an AND gate has changed, there's a certain delay before the output is changed accordingly. That particular delay is called the propagational delay. If you go all the way back to the NAND gate, that's using two P transistors and two N transistors, that particular circuit has a delay as well. Okay, so when you change the input of that NAND 2 gate, the output will change after a certain delay. Now that delay is really short. Okay, it's a very short amount of time, but nonetheless, there is a delay. Are we kind of understanding the concept of propagational delay? It simply means that when the input changes, it takes a certain amount of time before the output changes accordingly. Alright, so let me look at the text channel. So was N-type transistor and P-type transistor only for the NAND gates? In general, we will be using AND gates and OR gates. Alright, so about that question, if all you know, okay, if all you know is how to use two AND transistors and two P transistors to make a NAND gate, and then you have a bazillion tiny little N-type transistors and P-type transistors, okay, how are we going to deal with the problem of but tech, this is all this stuff here this stuff here, they are using AND gates, OR gates, and NOT gates, and all we can do is to make NAND gates out of 2P and 2P transistors. How are we going to solve this problem? Because I think that's what the law is asking. So this is where you need to make the connection, right? You need to make the connection, and this is also why I said, at the very beginning of the semester, the concepts, they all stack up. All right, so how do we answer this question, people? Come on, how do we answer this question? All we know is how to make NAND gates, out of 2P and 2 N-type transistors. But now it seems like we need to make, AND gates, OR gates, and NOT gates. How do we solve that problem? And Eric is right. Okay, so without getting into the details, which you can get to if you want to, going back to the first lecture, okay, going back to the first lecture, maybe the second one, and also the associated lab, we know how to make a NOT gate out of a NAND gate. We know how to make a AND gate out of some NAND gates. I cannot remember how many. I think there are 2. And we also can make OR gates out of NAND gates. Once again, I think it takes 2 to make that happen. So the bottom line is, oh, okay, so maybe it's a little clumsy. Maybe it's unnecessarily using, maybe it's using more transistors than we actually need to, but we can make it happen. Just give me a bunch of P and N-type transistors, and I can make AND gates, OR gates, and NOT gates, just because I know how to make NAND gates. Now, this is why it is important to connect all of these concepts, because it is going all the way back to the beginning, going all the way back to week 1, and these concepts are not disjoint. Okay, they are all connecting to each other, and how that connection can be made in your mind is the big question. Okay, I cannot really answer that question because I can try the best I can to kind of remind you guys, okay, this connects with that one, that connects with that one. But how my mind works and how your mind works, I have no idea. I'm not a psychology major, so I can only address that question up to a certain point and then go like, I can't do past that point. All right, so anyway, yes, so Eric is correct, and so is Igor. Okay, so yeah, so making that connection is really important. I'll try my best to tell you guys how I make that connection, but sometimes that just happens in the in the background, so it's not a very conscious process to make that connection. Okay, so that's a tough question to answer. All right, so now we basically what I'm saying here is it takes one propagational delay to get all of the G bits. It took and at the same time, okay, during that one propagational delay, we can get all the P values as well. So all the GI value and all the PI values, they can all be done within one propagational delay from the time when the X and Y and K0 are presented to the circuit. Are we doing okay with that concept? That okay, so time 0 we have X, Y, and K0 presented, and then at one propagational delay after that, we end up with all the G and all the P bits. Are we good with that concept so far? All right, so it's time to take row because my watch just buzzed. So we're gonna go take row, and this also gives you guys a pause, a time for your brain to recover. And today is 2-1 right there. And I cannot remember. It's visible now, but I cannot remember what word I have chosen to use. I just edited this earlier, okay, and I cannot remember how I changed it. All right, so there we go. The word for row taking is look ahead, and I'm going to put it into the text channel. Copy and paste. There we go. All right, so I'm gonna give you guys a little bit of time to do the row taking activity. Kind of consider this as a short break, like really short. And then we're gonna get back to this kind of messy stuff. All right, so while you guys are doing that, I'm gonna put in some more notes here. Okay, time 0. Xi, Yi, and K0 are presented as inputs. Okay, one propagational delay later, we can get all the P and the G bits, right? So we can get all the P of I and all the G of I computed. So I'm just using the abbreviation here. Okay, let me just kind of make it clear what this is. So PD is just propagational delay. And obviously I am making the assumption that the AND gates, OR gates, NOT gates, they all have the same propagational delay. It's not like that in reality, but it doesn't really matter, for what we are trying to talk about. So we can make that assumption. All right, so now let's take a look at how we compute K1. Okay, K1 depends on what? It depends on G of 0, depends on P of 0, it depends on K of 0. Now K of 0 was available from time 0, okay, from the beginning. So there's no propagational delay to worry about with K0. But what about G0 and P0? Well, they take one propagational delay, right? So if that is the case, okay, how many additional propagational delay do we need on top of, basically from the time when all the G and all the P's are computed? How much more time, how many more propagational delay do we need in order to compute K of 1? That's a question. I want you guys to think about it, but think about it in the sense of logic gates. Okay, what can happen at the same time, and then what dependency says, oh, okay, but you can't really get to that one until these guys are ready. And Tam is correct. It's 2 propagational delays. All right, so I'm gonna write down here. Okay, so 2 PDs later. Okay, I'm gonna switch back to this one here. So 2 propagational delays later, we can get P0K0 done, right? Okay, so I'm gonna use nested bullet points here, because there will be some other things later on that we're gonna add. Okay, so 2 propagational delays later, we would have P0 and K0 done. Okay. So are we doing okay so far? Are we kind of associating the propagational delay with the structure of the expression? Because this expression here has an implicit pair of parentheses around P0, K0. Because I'm preserving the priority of operators, so conjunction and multiplication have the same operator priority, and then addition and disjunction have the same as well. So we always perform the multiplication or conjunction first, and then we perform the addition or disjunction in this case. So are we good with that with that concept? Because I'm not using extra parentheses when I don't need to. And those are, by the way, the same priority of operators in C and C++. So, it really should not come as a huge surprise here. All right, so Chris posted the question. So a PD, a propagational delay, could be described as how long the previous calculation takes to run through the required gates. It's just one gate. One propagational delay time is only for one gate. So from the time the input of a gate changes to the time that the output is correct for that input, that is the propagational delay for one single gate. And when I use the term PD, it is always for one single gate. All right. Yes, so one PD is for one gate. Or if you want to be more specific, I can make that more specific as well. So we can say one GPD, which is gate propagational delay. Okay, so now it is very specific to be applied only to a single gate. All right. So two gate propagational delays later, we would have P0 and K0 done. Who needs that? Who needs P0 and K0 to finish the calculation? K of 1, right? K of 1 needs that because we need the output of this AND gate as well as G of 0 in order to perform the last operation, which is the disjunction here. So that means, after one more propagational delay, we will have K of 1 computed. Okay, so I'm going to switch back to here, and then we'll specify that and say, oops, right here, 3 gate propagational delays later. In this case, we'll have G0 or P. Okay, let me just put in extra parentheses, just for in this context, so this way it is extra clear that we perform the conjunction first and then we perform the disjunction. All right, so is that okay? Does everybody understand, how at time 0, we got all the inputs, and then at 1 GPD later, we got all the P and all the G, bits computed. After 2 gate propagational delays, we got the conjunction of P0, K0 done, and then after 3 gate propagational delays, we finally get K of 1 done. So are we good here? And I'm just going to make this also extra clear that this is K of 1. So K of 1 is done within 3 gate propagational delays from the time that X, Y, and K0 are presented. Alright, so Tam said there's a possibility that one propagational delay can calculate multiple gates in parallel. Yes. Remember, all the gates are sitting there and they can all be computing at the same time. So the only thing that we can say, but what about those things, they cannot be computed at the same time, is when we have a dependency. Okay, so what do I mean by a dependency? So when you have an expression that looks like this disjunction cannot be computed until the conjunction is done. So with this kind of dependency, you have to introduce one more propagational delay on top of how much time it takes for P0, K0 to be done, because this disjunction cannot start until P0 and K0 is done. So are we good so far? Alright, cool. Alright, so now we're going to look at K2, okay, because we are done with K1. K1, the whole thing, the whole shebang, it can be done in 3 gate propagational delays from the time that X, Y, and K0 are given to us. Okay, cool. So now we look at K2. Now when you look at K2 and K3, do not look at the derivation, okay, the expressions in the derivation. They're only here to show you how we got here. It is the last one that is important, because every semester, guess what? Someone is going to design the circuit using one of these two expressions, and that would not be right. Okay, if we only want to use these two expressions, why would I bother with the third one, right? So there's a reason why we have a third one, because that's the one that we want to use. Alright, so if you look at K2 like this, okay, and we're going to go back to, I'm going back first, you can stay on this page. So I'm going to go back and say, after 2 propagational delays, what else can we do? Well, as it turns out, after 2 propagational delays, since X, Y, and K0 are presented, we can do this and also this at the same time, because in order to compute P1 and G0, we just need to make sure that P1 is computed and G0 is also computed, but those two are computed at the same time at 1 propagational delay, since X, Y, and K0 are presented. So with 1 more propagational delay, or 1 more gate propagational delay, we can compute the conjunction of these two terms. And it's the same thing over here. So even though this one has 3 inputs, it's okay, because you can have multi-input pin gates. Okay, so the AND gates can have 2, 3, 4, 5 inputs. It's not a problem. So now we are looking at a 3-input AND gate. Okay, P0 itself is going to take 1 GPD. I take it back. P1 is going to take 1 GPD. P0 is computed in the same amount of time, right? So when P1 and P0 are done within 1 GPD, K0 doesn't require any time because it's just an input. So when all 3 terms are done within 1 GPD, then we just need 1 more in order to compute the conjunction of these 3. Are we doing okay so far? I'm going to type this on the other side, but I want you guys to think about this, okay? So that, when you are Okay, I am getting really lazy, so I am just going to. Oh, I cannot do that. Not easily. I was just about to copy and paste from my own page. That turns out, it might be just faster for me to write this out myself. But I want you to think about what I just said a little bit earlier. Alright, so I am done typing on the other side. So 2 gate propagational delays later this one is only useful for the computation of K1. These two are useful for the computation of K2. Are we convinced that these 3 conjunctions can all be done at the same time, exactly 2 GPDs after X, Y, and K0 are presented? Because this is the jump, okay? This is the jump that goes from, oh, we can do this with K1 only because K1 is simple. No, we can do this with K2 as well because the conjunctions can all happen at the same time. Because we are using 2 different AND gates. Here's one AND gate, and this is another AND gate. These 2 AND gates can compute at the same time. So are we good so far? Are we convinced that 2 gate propagational delays later, now we got 3 results done? The first one is only useful for the computation of K1, but these 2 are useful for the computation of K2. So I'm going to let you guys think about that a little bit, and then I will switch back to here. So if you have any questions, you might want to ask at this point, because the key to understanding all of this is basically to say, oh, okay, the gates can all compute at the same time. That really is the key. But then, if one gate relies on the result of another gate, then those cannot happen at the same time, because you have to wait for one to be done, and then the next one can start. Alright, so there are no questions. Okay. Alright, so now we can now see that G of 1 is ready after 1 GPD. This conjunction is ready after 2 GPDs. This conjunction is also done after 2 GPDs. So in the worst case of all of these 3 terms, G1 is 1 term, P1 G0 is 1 term, P1 P0 K0 is 1 term. Of these 3 terms, the worst are these 2, which will take 2 GPDs. So at the end of 2 GPDs, we would have all 3 terms ready. So this last addition here, or the last disjunction, is also 1 gate, because you can have a 3 input OR gate, and it is still 1 gate, and it will still only be using 1 GPDs. So with 1 extra GPD, we can now compute K of 2. So I'm going to type on the other side, and you guys can kind of look at this and see if you have any questions. So K of 2 being G of 1, or P of 1, G of 0, or P of 1, P of 1, P of 0, and K of 0 is done after 3 GPDs. So I'm switching over to the other side, just so that you can see what I've typed here. Alright, so because the individual terms for computing K2, they're all ready, they're all done within 2 GPDs, so the overall disjunction is going to take 1 more GPD for a total of 3 GPDs. So 3 GPDs after X, Y, and K0 are presented, we would not only have K1 computed, but we'll also have K2 computed. So No. Okay, so Tam, the whole point of this whole thing is K3 is also going to be done within 3 GPDs. K4 is going to be done within 3 GPDs, even though they look uglier and uglier and uglier. But it does not matter because we can, assuming that we can have, AND gates that can have like a bazillion inputs, as well as OR gates that can have a bazillion inputs, and all of those would take only one single GPD once each, then it doesn't matter what K what we're talking about. It can be talking about K64. It just looks really super duper ugly. But each term, okay, there will be one term that is just a G, and then there's a whole bunch of conjunctions, and all of those conjunctions will only involve the P and the G and also K0, and all of those are done within 2 GPDs, and that's why within 3 GPDs I can compute any carry bit. That is the whole reason why we went through all the Boolean algebra and all the reasoning and all the expansion of the terms and whatnot, is basically to get to this point and go like, oh, so all the carry bits can be expressed as a single G term, a bunch of, and then okay, let me take that back. All the K terms can be expressed as the result of an OR, and then each component of the OR can be either a single G term, which is not a problem because we got all the G terms within one GPD. But then the other ones are basically a bunch of conjunctions of the P and the G's and the K's and the K0, and all of those can also be done, one GPD after we get, all the P and the G terms done. So each conjunction is done within 2 GPDs, and then we are ORing, all of these, the result of all the conjunctions. That one OR is going to take one extra GPD for a grand total of 3 GPDs. All right, cool. And this is called carry look ahead. As you can probably imagine, when you get down to K3, it's going to look uglier. Okay, you will need more AND gates. You're going to need a OR gate that has more inputs, but it's okay because we are still making that assumption that each gate only has one single GPD as a delay. All right, so you just kind of, even though things look a little bit uglier, when you get to the like K4, K5, and so on, they will still only take the same amount of time, which is 3 gate propagational delays after X and Y and K0 are presented as inputs. Are we good so far? Alright, so is the last conjunction important if K0 would usually just be 0 in our case? So in these calculations, K0 is an input pin. It is not assumed 0. It is just an input. So K0 is an input. All the X bits are inputs. All the Y bits are inputs as well. So that's why I said at time 0, all the X, Y bits as well as K0 are presented as inputs, and that's our mark. That's where we start to count time. Okay, and within 1 GPD we got all the P and all the G terms done. Within 2 GPDs we got all the conjunctions of the terms done, and then within 3 GPDs we got all the K terms done. Because there's no linear dependency anymore. K3 does not really depend on K2 anymore because we basically use the technique of expanding the terms so that K of 3 is, K of 3, even though originally it relies on K of 2, but because we know how to express K of 2 in the P terms, G terms, and K0, we expand it, and we just basically say, oh, but if we have P2 time conjunction with this stuff here, we can use distribution. So the key to this whole thing really is distribution, okay? Because once we apply distribution, we don't have the dependency anymore. We just end up with, oh, this is an AND gate, oh, this is another AND gate, oh, this is yet another AND gate, and they can all do ANDing at the same time. The only thing that cannot be happening at the same time is the overall OR, because the OR depends on the result of each individual and that's why we have that extra, GPD on top of, the GPD to compute all the conjunctions. All right, so we are running almost out of time, okay, but I think I got all the key concepts out, for the lab that you're going to be doing tonight. So, but before I kind of let you guys loose to start on the lab, do we have any questions about the concept that we are talking about today? The main concept is how to translate an expression into logic gates and how to make these logic gates to carry out calculations in parallel as much as possible. Alright, so while Eric is typing, I am going to let you guys look at the key to get into the access key to tonight's lab. And I will get to Eric's question in just a little bit. Let me first get to the lab first. There we go. So tonight's lab is called 3x3 Carry Look-Ahead Adder Part 1. And there are two parts to it. So there is the lab portion, which is in the form of a quiz. And there's also the file submission. And both are due tonight. I know somebody's going to ask, are we going to do have to turn it in tonight? Yes, you have to turn in the file tonight. Alright, so let's go ahead and take a look at the access key. I cannot remember. The key is 3x3 part 1. I'm going to copy and paste it also into the text channel. So there you go. There's your access key. And since the quiz is now visible, you guys can get started now. And I'm going to say show correct answers at today after it is due, like that. And I do this because this way, if you guys want to go back and use the lab as study material, you can. I think if I don't do this, you would not be able to look at the quiz again. I'm not sure, but I know for sure that if I do this, you guys can go back and use the lab as study material as well. Alright, so the labs are assigned, and the homework assignment that collects the file as the result of tonight's lab, that should be open as well. That one does not have an access key. Alright, I'm not seeing any questions in the text channel. Good. Okay. So on Thursday, so I'm going to give you a preview of what we're going to do on Thursday. So on Thursday, we are going to go back, okay, because we talk about how we can implement carry look ahead. So on Thursday, I'm going to go back and actually show you what a carry ripple adder is going to look like. The one that is slow, okay, so we are doing the one that's fast but more complex first, and then on Thursday, I'm going to show you how I would do a carry ripple adder. That is really slow, okay, but it's nice, it's good looking, but it's really slow because it just depends on the carry bit to propagate along a chain, and that's why it is slow. All right, so I'm gonna stay on for maybe another minute or so just to see if there are any questions. If not, I'm gonna stop the streaming. And then we back in about 5 minutes after I grab something to drink, and then I will start to answer questions. Hopefully not questions that well, I'm not gonna say it, but we'll see. We'll see what kind of questions I'm gonna get. Alrighty, doesn't seem like there are any questions. I can't find my little. I bought a little thing, that has a bunch of sound effects on it, and one of them is crickets. So it has crickets as one of the sound effects. So when I ask the class, do we have any questions, and nobody says anything, I would play that button. But I have misplaced it, unfortunately. I bet you I can get a phone app to do the same thing. Alright, we got a few people typing, and I'm just gonna wait a little bit longer, before I stop the stream. And all right, I will try. I just keep misplacing my stuff. That's one of my special abilities as well. Yep. Alrighty. So it doesn't look like there are any conceptual questions at this point. Now the cats, it doesn't taste like something that they would eat. They're smart. They just, yeah. Alrighty, I'm gonna stop the stream, and I'll be back in about 5 minutes to answer